All right, I'd like to go one more problem in Chapter 7 before we start in Chapter 8. That's problem 743 on pages 226. It says determine the maximum possible load power for the circuit shown in figure 758. Here you got a voltage source. Here on this side you got a current source on the right, and your load is a potentiometer in the middle. And that was the application of maximum power transfer to the application of Thevenin's. So what we need to do is come up with a Thevenin equivalent for the circuit. So everything outside the load then would be considered the network A. And then to come up with a Thevenin's, first let's calculate R Thevenin. And looking at R Thevenin, you look at a terminal X and Y. And with the network A de-energized, so if there's a voltage source, we got to put a short circuit there. If there's a current source, you need to open circuit it. So all the voltage sources will be short circuited, all the current sources will be open circuited. And you look at the terminal X and Y. If I look at that, we can redraw the circuit. This is open and this is short circuited. So if this is open, 200 and 100 be connected in series, so be 300. And if you look at terminal X and Y, you can actually flip this over. If you've noticed, the 120 and 300, they're connected. They have two nodes in common, point X and Y, so really connected in parallel. If you don't see it that way, you probably need to redraw it. So to flip the 300 from the right to the left side of the circuit, point X and Y, and you can see they're really all connected in parallel. So that'd be a product over the sum. That gives you 85.71 ohms. To calculate V Thevenin, you need to open circuit it at a point X and Y. That would be V open circuited. So V open circuit would be V Thevenin. At this point, you need to decide which technique you're going to apply to solve the circuit. There are a number of ways you can do it. One of the technique that we did, it was called current to voltage transformation. You got a current source, you can replace it with a voltage source. And the way it is, if you have a resistor connected in parallel with a current source, you multiply the resistor by the current, give you R of S, I of S. And then the current is always leaving the positive polarity, so it'll be plus or minus like that. And that's exactly what you have here. So the voltage source would be 100 times 80. That's 8,000 millivolts, which gives you 8 volts. But would be minus plus polarity. So this would be minus here, be plus here, 8 volts. And then you put a resistor 100 ohms connected in series with. So this is point A and B. You're going to replace it with this circuit right here. Now, if I go around the loop, now this is open circuit, so you got a single loop now. All the voltage should add up to 0. That's Kirchhoff voltage law. When I do that, I can calculate what the current I is. So from here, start from this point, minus to plus. That gives you plus 5 volts. Everything else will be negative, minus 120 times the current I, 300 times the current I, minus plus is also plus, gave you 8 volts. So from here you calculate the current I, which is 13 divided by 420, 300 and 120, and then 5 plus 8. And then there's a couple of ways you can calculate V Thevenin. If I go around the yellow loop, I'm sorry, the blue one, that voltage is, again, you can apply Kirchhoff voltage law for that loop, and that should add up to 0. So it'll be plus 5 volts, plus minus, it gives you minus the current I times 120, and then plus minus the V Thevenin. Or you could have done it in this loop right here, it doesn't really matter. So if you do that, V Thevenin would be equal to 5 volts, and you can see it's minus plus here, plus minus, so the voltage 5 volts will be across 120 ohms, and then plus V Thevenin. but if you don't see it, that's the best way to do it. Just write a single loop. So it'd be 5 minus the current I we calculated with 13 over 420 times 120. That gives you 1.2857 volts. And then maximum power transfer, we come up with this equation, is equal to V Thevenin divided by 4 times R Thevenin. Again, please be careful with this. The R Thevenin is not a square, it's just a V Thevenin. We got those values. V Thevenin is 1.2857, and R Thevenin we calculated to be 85.71. That gives you about 4.82 millivolts. We have this set of homework problems, and I think that was the last one that I want to work out. Please email me with any questions you have in Chapter 7. I'd like to start in Chapter 8, starting in new topics, and then in magnetic circuits, in Chapter 8, magnetism and electromagnetics. Before we do that, so far we did talk about the charges. There's a good analogy between electrical field and a magnetic field. So I'd like to talk about electric field just for a couple of minutes. If you have a charge Q1 and Q2 at point 1 and 2, is very similar to the gravitational force. If you got two masses, M1 and M2, there's a gravitational force between the two, just like a solar system. There's a gravitational force between the sun and the Earth. It's the same thing is true at any two mass, or is also is true with what's called electric field force between the two charges. So that there's a force in the direction of radius R12. If it's a vector between Q1 and Q2, definitely there's a force in that direction, which is equal to charge Q1 times Q2, force F2, divided by 4 pi epsilon sub 0 times the radius R12 quantity squared, where epsilon sub 0 is called permittivity of free space or air, which is 8.85 times 10 to the minus 12 farads per meter. Is a constant quantity. And then Q1 and Q2 are in coulombs, and the radius R12 is in meters, then the force is in newtons. Now, if I start moving the charge 2 around, every place that you move it, there's an indication there's an existent force, and so there's a field of force by moving the charge Q2. So if I let charge Q2 be the test charge, call it Q sub t, then if I look at this equation, divide both that equation by Q2, or Q sub t in this case, then you end up with Q1 4 pi epsilon sub 0 times R12 quantity squared. By definition, that's the electric field, because a force per unit charge by definition is equal to electric field. So there's a force. Now it's only a function of Q1 only. So if there's a charge, then definitely you have some kind of electric field. And that electric field does have some kind of a force, which can be calculated per unit charge. So electric field intensity, E, is newtons per coulomb, and that's force per unit charge. A very good example would be if you take two parallel plates and separate it by a distance d and apply a voltage to it. There's like a capacitance. There's an insulator between the two plates. It could be air or some kind of insulator, glass or ceramic, whatever, any type of insulator. Air is a good insulator. So if you do that, then you can calculate what the electric field is. In this case, electric field would be equal to, with a little bit of manipulation, it does comes out to be equal to the voltage that you apply. We're going to get into this later in chapter, I believe this is chapter 12 or 13 when we talked about electric field and capacitance and inductance. So be equal to applied voltage divided by the separation distance d. I think we did talk about this briefly. So one of the examples of electric field is lightning, which is happening a lot here in Florida. When the clouds are moving in the sky, due to the friction, they pick up a negative charge, and then the earth becomes a positive charge. Then you form an electric field. Now, if you pick up too many charges, what happens then, because of the electric field, there's a force that would be equal to electric field times the electrons for each atoms of the insulator. In this case would be air in case of a lightning. What that really does, if you have too much force, it will break up the bond between electrons and and air molecules. And then they free up the electrons, and then at that point the air is called to become ionized. And then you have a huge, start conducting if you have a free electrons, and you have a very high current. 1,000 amps is typical, and about 1 million volts develop between the cloud and the earth. And again, 1 million volts it's not a voltage actually. It could kill you. It's electric current. 100 milliamps can easily fry you, but 1,000 amps is extremely dangerous. But if you look at the magnetic field intensity, H, the only difference is with electric field, the field always starts from one charge and it will terminate on another one, in this case the plates. But the magnetic field, there's no starting and no ending point. It's a closed loop. So if you take a piece of conductor like this, and that is carrying a current I, in this case let's say it's a DC current, constant current. If you put your thumb in a direction of current flow, and then your fingers, the right hand rules, your right hand, the fingers, they give you the direction of the magnetic field. So in this case, if the current is flowing in that direction, that's the direction. That's where you put the right hand right here, and that's your thumb, and then this will give you, you wrap around your fingers, it give you direction of the magnetic field intensity H. There's a lot involved with this. You have to use this closed loop integral to calculate all of this, but what it really comes down to, this is called Ampere circular law, that the magnetic field intensity H is equal to the current I divided by 2 pi the radius r. So the farther away from your conductor that you're carrying the current I, you're losing the magnetic field intensity. So here it would be maximum, and as you get farther away, moving away from the conductor, just like the power lines, they say it's dangerous to be very close to the power line because of the magnetic field intensity H. Now that's if you have a single conductor, but in most applications, all the transformers, rotating machines, generators, and motors, you have a number of turns, which they call a coil. So if you got a bunch of coil, you can then, and you have a current I flowing through it, you're going to generate a magnetic field. In this case, you still use the right-hand rules, but here you wrap around your finger in the direction of the current flow. So in this case, your finger will be going into the screen, and then your thumb will give you the direction of the magnetic flux. It's the exact opposite. So if this current is flowing that direction, it's coming out, going that direction to the right, then the magnetic flux would be going upward directions, and like that. This equation for one single conductor, but if you had n turns in your coil, then the magnetic flux, magnetic field intensity H is equal to n times I 2 pi times r. That means the total current enclosed by the coil. I don't know, you might have this already done in your physics class. If you take a piece of permanent magnet like this with the North Pole and the South Pole, and put a piece of glass on top of it and put a bunch of iron bits. And then you can see they line up such that there's a line of magnetic flux coming out of the North Pole, and it will enter the South Pole. But it does not start here and it will terminate here. Actually, it does go to the permanent magnet itself. So they're all closed loops. They call these line of magnetic field flux, just to give it physical meaning. They don't really exist physically. But there's a force. If the magnetic field wasn't so common, then everybody thinks it's probably some kind of a magic. But it's not. It's just there's a magnetic field, and the magnetic field world does have a force. Now, again, to give it some physical meaning and to be able to measure the magnetic field intensity, there's a unit called Maxwell's, after Mr. Maxwell's. There's not much you can see in a magnetic field that is somehow is not related to Maxwell and or Gauss. Maxwell was the one first we used partial differential equation. It's called a Maxwell's equation to be able to describe or explain how the wave is propagated in air to the wave, magnetic waves. Now, the unit for magnetic field intensity, H, in terms of Maxwell's, which is the line of force, by definition, if you look at 1 square centimeter, then they give you a magnetic field density. There are actually three variables that we look at in magnetic field. One is the H, which we just talked about here. That's your magnetic field intensity, which is a measure of magnetic field. How much magnetic field do you have? There's another one called phi, or the flux. Those are the line of magnetic field. And then there's one called B. That's your magnetic field density. So there are three different things. This is the measure of magnetic field, H is. Phi is the magnetic flux, and B is the magnetic flux density. That really gives you the strength of the magnetic field. So magnetic field density, B, is the strength of the magnetic field, which is measured by number of Maxwell's, the number of flux lines that you have per square centimeter. And that's after Mr. Gauss. So by definition, 1 Gauss is equal to 1 line of magnetic flux per square centimeter. So if you take 1 square centimeter and put it inside the magnetic field and count the number of magnetic flux that are going through it, then by definition that will give you the density, how dense is your magnetic field. Of course, if you have 1 line of flux, then you have a really weak magnetic field, so the density is low. But if you have 100,000, then you have a high magnetic field density. Now in this example, you got 1, 2, 3. So the magnetic field density is equal to 3 Gauss. Gauss is an older unit. It's very small. They came out with a new unit is used for magnetic field density. B is called Weber per meter square, or Tesla. So 1 Weber instead of flux, instead of Maxwell's, the line of flux, they're going to use Weber. Well, Weber is just a larger unit. Instead of 1 line of magnetic field, now you have 100 million, or 10 to the 8 line of magnetic field. By definition, that's equal to 1 Weber. It's just a larger unit. Instead of measuring per square centimeter, then you're going to count the line of magnetic flux that you have per the square with 1 square meter area. The cross-sectional area of your 1 meter square. And that's known as Tesla. So Tesla, if I calculate Tesla, then B would be equal to 10 to the 8. 1 Weber is 10 to the 8 Maxwell's. Meter square is 10 to the 4 square centimeters, because 1 meter is 100 centimeters. If you square both sides, 1 meter square, then you get 100 square, which is 10,000, which is 10 to the 4. Now, 8 and 4 will simplify. That gives you 4, 10 to the 4 Maxwell per square centimeter, and that's by definition that was Gauss. So magnetic field density in Tesla, then it simply be equal to 10,000 Gauss or 10,000 Maxwells per square centimeter. Okay. So that should be B in Tesla is equal to 10,000 Gauss, or just Tesla is Weber per square meter. Either one is the same definition. Now, the Earth has a very weak magnetic field, and it's about 50 microtesla. So it's extremely small, but if you take Tesla to be 10 to the fourth, so you can see the magnetic flux density B in Gauss would be only a few for Earth. Now, it turns out that there's a strong relationship, there's a correlation between magnetic field density B and the magnetic field intensity H. It's known as a BH. All the manufacturers, when they manufacture the ferromagnetic materials to be used in transformers or any type of rotating machines, they give you what is called a BH curve. It gives you the correlation between the magnetic flux density B and the magnetic field intensity H. That's known as permeability, and we're going to see in a minute what does the permeability actually represent. It's just a measure of how easy it is to take any ferromagnetic materials and make them or convert them into the permanent magnet. The permeability is equal to mu sub r times mu sub 0. Mu sub r is called relative permeability, which is anywhere from 1 to 50,000. If it's air, then mu sub r is equal to 1. If it's other magnetic materials, it could be up to 50,000. Mu sub 0 is called permeability of free space or air, which is 4 pi times 10 to the minus 7 Henry per meter. Just like we had electric field epsilon sub 0, which was 8.85 times 10 to the minus 12, as a constant to represent the permittivity of free space in case of an electric field. Mu sub 0 is another constant that it gives the permeability of air, which is 4 pi times 10 to the minus 7. So again, there's a strong analogy between electric field and a magnetic field. Well, we need to look at to see what is the source of a magnetic field. There are some materials such as glass or wood or what have you, plastic, that can never become a permanent magnet. The reason is if you look at the atoms, you have the nucleus in the middle and the electrons in orbit. They're orbiting the nucleus at the same time that they're spinning around themselves, either in a clockwise or a counterclockwise direction. Now, every time you have an electron that is spinning about its own axis, it will generate a very weak magnetic field, just like Earth. This is your sun, and this is the solar system. The Earth is going around the sun 24, is spinning 24 hours. At the same time, it is orbiting the sun 365 days. So when it's spinning about its own axis, then it generates a very weak magnetic field. Now, for the materials such as ferromagnetic materials, the number of electrons that go in a clockwise direction is not identical. It's not the same as the electrons going in a counterclockwise direction. Then there's a net result that generates a very small magnetic field. It's called the domain. In case of a ferromagnetic iron, is only one extra one that is going in the opposite direction. The rest of them will cancel each other out. Now, if you have 10 to the 15 of those electrons that's extra, they will generate a magnetic field in the same direction. It's called a domain. Now, if you take a big piece of steel or any type of like a cast iron, and if you look at those domains, they all scatter all over the place, and then they will cancel each other out. If you give a piece of steel that it gets hit by lightning, or you take another permanent magnet and slide it over, what it really does, they line up those domains so that all of them will be north-south probably in the same direction, so the magnetic field will add up. So that's really the source of a magnetic field. The other thing you can do is to take a piece of ferromagnetic materials with all those domains that are scattered, so that's not really a permanent magnet, there's no magnetic field there. You can take a piece of wire, like a telephone wire, gauge 22 or 20, and wrap it around it. Here it is. You got a piece of, like I take a ring, it could be solid or it could be hollow. If it's solid, then we'll see you're going to have more magnetic field. But if it's hollow, you have less magnetic field. If it's air inside it, because that's relative permeability. Let's take a variable power supply. You always want to put a resistor here to limit the current, so you don't want to drain your battery, drain your source. And so say this is plus or minus, and hooked up to this piece of wire that you wrap it around like a coil. Now if the current is flowing that direction, it's going in, then you put a right hand rule, you wrap it around that, and then your thumb will give you the direction of magnetic field. So you'll have a magnetic field going in that direction, clockwise direction, inside that piece of steel. When you do that, then you really line up those domains, and now if you remove it, which we're going to see in a minute, is what is called a residual magnetization. This thing will become a permanent magnet, and they will all locked in. So we already looked at this. The ampere circle law for H is equal to N times I divided by 2 pi R. Now B is equal to mu sub M, that's permeability times H. So if I look at those two equations, we can look at the BH curve for this simple piece of steel. So here's your H. Initially, when the voltage is 0, so you're just going to turn this thing off and you're going to turn it on, start at a 0. According to this, if you start varying this voltage, and then you got a current I, which is equal to voltage divided by R. You can control it by the resistor, or you could put a constant voltage here and put a variable resistor in there. So here it is. You're going to start out with 0. You generate the magnetic field intensity H, and then you multiply by mu sub R. It gives you B. So at every point here you have H and B, and you keep increasing the voltage, the magnetic field intensity is going to go up, and the magnetic flux density also is going to go up. But it reaches a point that by increasing the voltage, now the current is going up, the magnetic field is going to go up, but the B stays the same. That's called a saturation. At that point, you can no longer generate any extra magnetic field, and the magnetic field density then per square area become a constant. It's called saturations. Now, at this point, you want to reduce the voltage. So if you start reducing the voltage all the way down to 0, unfortunately, the way ferromagnetic material is, it's not going to come back to 0 again. As soon as you start reducing the voltage, the magnetic field intensity H will get smaller, and when the voltage is completely down to 0, when the current is 0, the H is equal to 0. You'll be at this point. But at that point, you still got the magnetic field density B, which is a little bit smaller than what you had here, and that's called B sub R at this point. That's called residual magnetization. It's because of this residual magnetization that this thing becomes a permanent magnet, because those domains will lock in. Now you have a constant magnetic field per cross-sectional area, and you can no longer reduce it. Now to get rid of that, you need to apply a negative energy. So if I reduce the current in opposite direction, change the polarity there, then what it really does, the H is now is negative H, but the magnetic flux density B will come to 0. Go down to 0. But if you keep reducing the current I, or negative current, it does reach negative saturations. At that point, you keep increasing it again, positive. It doesn't come back to 0. It will go back to this loop when the current is down to zero again, the H is zero, but you still have residual magnetization at B minus B sub R. And if you keep increasing the voltage, it will go back up to the saturation again. This shaded area, or this area inside this, it gives you the energy losses that you have to put in, or the energy that you locked in that you can never get back. And that's called hysteresis. Hysteresis is a Greek letter, a Greek word meaning lagging behind. You can see the magnetic flux density B is actually lagging H, the magnetic flux intensity H. So B, when you come back here, H is down to zero, but B is actually lagging it by these residual magnetizations. One of the things that you want to do is this area here, again, the hysteresis area, is due to the losses or the energy you have to put in to make that permanent magnet and lock in those domains inside the ferromagnetic materials. Now, power companies, one way to reduce this, the manufacturer of the ferromagnetic materials, when they build the transformers, to reduce this, they add some impurity of silicon, about anywhere from, that's not 2.3, it's actually from anywhere from 2 to 3% impurity, such that it minimizes this area. Because if you're building the power transformers, there are three-phase. I'm looking at a single phase here. Here's the voltage generated here is anywhere from 18,000 to 24,000 volts from your steam turbines that convert that energy into the voltage, convert the potential energy or the kinetic energy, depends what type of a power plant you have. Will convert that into the electrical energy, which is about 24,000 volts maximum. But in order to reduce the transmission losses, the power company, the jack of voltage is about 765 kilovolts. To do that, they use transformers, and these transformers, they're not 100% efficiency, because you go from input to the output, from the primary to the secondary, but they really do it a three-phase, but not a single-phase, because you can take three single-phase transformers, hook up them with three-phase. What that really does, when you're talking about megawatts of energy or power, then you want to make sure your transformer is as efficient as possible. To reduce or to increase the efficiency, then you want to reduce this hysteresis, because again, that's the energy that you have to put in to generate a magnetic field, and it's not going to get transformed, that gets stored in, and it's not going to get transformed from a primary to the secondary. So anywhere about a 98 to 97 to 98% efficient. And then when they get to the residential area or distribution area, they drop it down to 34,000 volts, and then eventually to 208 volts or 120 volts, depends on the single phase or three phase or line to line or line to neutral voltages. They also have, if you open up, if you take a simple power supply and you open up the transformer, is also, they never use air. They'll have some kind of iron core, they call it, to wrap around the wire, which we're going to look at in a minute. And they use laminated. What that really does, and another loss is associated with transformers called eddy current, which is the heat loss in a transformer. And to reduce that, they put a sheet of laminations insulated, such that they put a large resistance on the path, so it minimizes the eddy current. So you have a very small current going inside the ferromagnetic materials iron core to reduce that heat losses. But we're going to talk about that more when we discuss inductances. Let's look at an example, problem 8.1 on pages 244. It says calculate the flux density for the shaded area in figure 827A. Assume that each line of the force represent 120 microweber of flux. They have their shaded area of 4 square centimeter, and if you count the line of flux that is going through it from the picture that I'm looking at in figure 244, you have 6 lines of magnetic force. So they want you to calculate magnetic flux density. Well, magnetic flux density is equal to flux phi divided by cross-sectional area. You have 6 line of magnetic flux is going through there from the picture, and that's per 4 square centimeter. So 6 times each line of force represent 120 microweber. So if you 6 times 120 microweber, that gives you the total flux going inside that 4 square centimeter divided by 4 square centimeter. Since they talk about Weber, then you need to convert the cross-sectional area into the square meter. So if you 4 square centimeter, each meter squared is equal to 10 to the minus 4 square centimeter. Square centimeter will cancel out, so you get 6 times 120 times 10 to the minus 6 divided by 4 times 10 to the minus 4. And that's Weber per meter squared. It gives you the unit, the new unit that we discussed, that's Tesla. So that gives you 6 times 1.2, 4 times divided by 4, or just simply 1.8 Tesla. So that's how you calculate magnetic field density given the number of flux that you have, and either per square meter or square centimeter you must do the conversion. Let's look at the magnetic circuits. Magnetic circuits are built using some type of ferromagnetic materials, and again we're going to see right now that why you want to use the ferromagnetic materials. Why not just use air? The reason is you can generate a very high magnetic field with a very small current. Now, if you take a voltage source here and put a resistor again, so you will not drain your battery, your source, limit the current, and let's say the current is going in that direction, coming out like that. So if you use a right hand rules, you wrap your finger around the direction of the current flow, your thumb on your right hand will give you the direction of the flux. So if the current is going in on top and coming around on the back like that, then the flux is going to generate in that direction. Now, unfortunately, there is some flux leakage. Not all the flux generated, because you can put another coil here, just to be single phase transformer. That see that with the transformers, they're not electrically coupled. There's no connection between the primary and the secondary, but they're electrically insulated, but they're magnetically coupled. And that transformation takes place due to the mutual flux that is generated by the current on the primary transferring into the secondary. So some of that flux is called a flux leakage, Phi11, and then the rest of them will be generated. It's going to go to the second coil. Right in the middle, we're going to call that the average length of the coil. So L sub C, average length of the iron core. So we can calculate the magnetic field intensity H using Ampere's law, Ampere's circle of Ni times L sub C, that's the average length. If you do a circular, it would be 2 pi r, but if it's non-circular, then you need to calculate what's the average length. But we had B is equal to mu sub m times H, so plug that in for H. It gives you mu and L sub C divided by. And then the flux B is equal to magnetic flux density B is equal to phi, the flux divided by cross-sectional area, and the area cross-sectional area will be the cross-sectional area here of the core. So phi will be equal to B times A. Phi is equal to A. We already have B, so we're going to plug the value of B from here to here. That gives you A times mu Ni divided by L sub C. I'm going to rewrite this. I'm going to take out Ni, which is equal to flux phi. Then you're left with L sub C times mu times mu sub m times A. So let's write this equation for the magnetic flux like that. Now, for a given ferromagnetic material or iron core, L sub C is constant, mu sub m is constant, cross-sectional area constant. I give you a piece of iron core like this. You can measure those. Those are all constant quantity inside the bracket. And if we define the capital R by definition, that's called the reluctance, is equal to everything inside the bracket will be L sub C divided by mu sub m times A. If I do that, then you get Ni is equal to flux phi times the reluctance R. Okay. And we can look at an electrical circuit. If you have a voltage V, connect up to the resistor, and you have the current I. V is equal to I times R, and V is electromotive force, EMF. This is for electrical circuit. Now, I can redraw this. I can draw a diagram for this equation right here. I'm going to make that a plus and minus Ni, and is equal to phi times the reluctance R. This is a magnetic circuit. And they call N sub I because that's your source of magnetic field. Here's the source of potential. This is voltage is a source of your electric current. Okay, so that's electromotive force. This is magnetomotive force. MMF is equal to force F. That's just by definition. And then the flux phi is very similar to the current I. And the resistance in an electric circuit is very similar to reluctance in a magnetic circuit. So every magnetic circuit you can draw the electrical analogy and be able to solve for whatever the flux or reluctance or whatever you're looking for. Let's look at this equation again. The flux phi is equal to Ni divided by reluctance. Let's see what happens with the reluctance. Well, the reluctance was defined as L sub C mu sub m times A. L sub C mu sub A times A. For a given piece of iron core, again, this is constant, A is constant, but what happens for mu sub m? If the mu sub m is very large, then what happens to the reluctance? If mu sub m goes up, if you take ferromagnetic material with a very high permeability, that means it's easy to turn those domains, line them up to make a permanent magnet, then the reluctance is going to go down, and the flux phi, if the reluctance goes down here for a given number of turns and a constant current, you're going to generate a much higher magnetic field. Well, mu sub m anywhere from 50 to 50,000. That's exactly what they do. If you use permanent magnet has a very weak magnetic field. So if you look at all the generators they don't use permanent magnet. They generate a magnetic field using a simple constant current. Okay, they apply what is called a field current. They apply a constant current, a DC current, to the field winding of your generator, and it has a very high permeability magnetic. Then you can generate a very high flux with a very small current based on this equation here. So the smaller the reluctance is very similar to the voltage. For the applied voltage, for a constant voltage, the smaller the resistance is, the higher current is going to have. The same thing as always true. The smaller the reluctance, that means a higher magnetic flux for the given MMF. And so you can generate a very high a very high line of flux. And later on we're going to see when we talked about Faraday's law. Faraday's law did a very simple experiment. The faster you cut the line of magnetic field, the higher the voltage is going to be. So the voltage is directly proportional in case of a power plant. in a generator is directly proportional to the speed, how fast, how much magnetic flux you have, and how fast you're cutting those line of magnetic flux. We're going to talk about that in more details in later chapters. All right, we'll stop here and we'll look at some problems in Chapter 8 next time.